Hello students. So in this solved example, we calculated the mole fraction of the components in the vapor phase. Now if we compare the mole fraction of the components in the vapor phase, this is the mole fraction of dichloromethane in the vapor phase, it is 0.82, and this is the mole fraction of chloroform in the vapor phase, which is equal to 0.18. Clearly the mole fraction of dichloromethane in the vapor phase is greater than the mole fraction of chloroform. Why is this so? This is so because this dichloromethane is more volatile than chloroform. And how do we know that dichloromethane is more volatile than chloroform? The vapor pressure of pure dichloromethane is 415 mm of mercury and the vapor pressure of chloroform is 200 mm of mercury. So vapor pressure of pure dichloromethane is greater than the vapor pressure of pure chloroform. Dichloromethane is the more volatile component in comparison to chloroform, because of which the mole fraction of more volatile component in the vapor phase is greater than the mole fraction of less volatile component. So at equilibrium, vapor phase will be always rich in the component which is more volatile. Now next topic, Raoult's law as a special case of Henry's law. Now this is the expression of Raoult's law and this is the expression of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a given solution is equal to mole fraction of the component in the solution multiplied by pressure exerted by the pure component. And according to Henry's law, in the solution of gas in liquid, the partial pressure exerted by the gas is equal to Henry's constant multiplied by mole fraction of the gas in the solution. So if we compare this expression for Raoult's law and the expression for Henry's law, we can see that this Henry's constant becomes equal to the vapor pressure exerted by the pure component or the vapor pressure of the pure component. So in this way, Raoult's law becomes a special case of Henry's law, in which Kh becomes equal to P01. Again, according to Raoult's law, vapor pressure of a volatile component in a solution is given by, this is the vapor pressure of the volatile component or the partial pressure of the volatile component, and this is equal to mole fraction of the component in the solution multiplied by the vapor pressure exerted by the pure component. And in the solution of a gas in liquid, the partial pressure is equal to Henry's law constant multiplied by mole fraction of the component in the solution. Now comparing the two equations, we find that Kh becomes equal to P01. Now what is P01? This is the vapor pressure exerted by the pure component 1. So in this way, Raoult's law becomes a special case of Henry's law. Now next, vapor pressure of solutions of solids in liquids. Now this is another class of solutions in which the solute is solid and the solvent is liquid. Now the examples of solid dissolved in liquid, for example sodium chloride, glucose, urea and cane sugar in water. Here sodium chloride, glucose, urea and cane sugar, these are the solutes and water is the solvent. Another is iodine and sulfur dissolved in carbon disulfide. Here iodine and sulfur are solute and carbon disulfide is solvent. Now the physical properties of the solution are quite different from that of the pure solvent. For example, vapor pressure of pure solvent will be different from the vapor pressure of the solution. Now what is vapor pressure of the liquids? Liquids at a given temperature. Now temperature has to be constant. At a particular given temperature, liquids vaporize, and under equilibrium conditions, the pressure exerted by vapors of the liquid. Now pressure exerted by vapors of the liquid over the liquid phase is called vapor pressure. See, this is the pure liquid. Suppose water. Now some of the water molecules are in the vapor phase. These blue dots represent the water molecules in the vapor phase, and evaporation is taking place from the surface of the liquid, and some of the water molecules are going into the vapor phase. So these are the vapors of the liquid over the liquid phase. This is the liquid phase and this is the vapor phase. So the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure. Now what happens In a pure liquid, for example in water, the entire surface is occupied by the water molecules, and these water molecules are escaping into the vapor phase, exerting the vapor pressure. Now suppose a non-volatile solute, for example sodium chloride, is added to a solvent to give a solution. Now if a non-volatile solute is added to a solvent to give a solution, now the solute is non-volatile means it does not go into the vapor state. The particles of the solute do not change into the vapor. So what happens when a non-volatile solute is added to a solvent? The vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. Why? When we add a non-volatile solute, since the solute particles do not go into the vapor state, then what happens? Some part of the surface is occupied by the non-volatile solute also. Now here the green dots represent the solute particles and blue dots represent the volatile solvent. Now here the surface of the solution is partly occupied by the solvent molecules and some part of the surface is occupied by the non-volatile solute particles, because of which the number of particles of the solvent or the number of molecules of the solvent going into the vapor phase decreases, because evaporation is taking place from the surface. Now in case of pure solvent, the entire surface was occupied by the solvent molecules, so large number of solvent molecules were escaping into the vapor phase. But in case of a solution of a non-volatile solute in a volatile solvent, or in case of a solution of a non-volatile solute in a solvent, what happens? The surface of the solution has molecules of the pure solvent as well as the molecules of the non-volatile solute, because of which the number of molecules of the pure solvent escaping into the vapor phase decreases, as a result of which the vapor pressure of the solution decreases. So in the solution, the surface has both solute and solvent molecules, thereby the fraction of the surface covered by the solvent molecules gets reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced, thus the vapor pressure is also reduced.